models is hard, and you may even move away from the Bayesian framework and become frequentist. And that's what, for example, Frank Freitas has been very successful at doing. He's using random forest, frequentist confidence intervals, and he's doing very well. And as I mentioned yesterday, if you haven't yet looked into, there's some papers on arXiv on using the bootstrap for Thompson sampling, and I think that's a fantastic idea. I think if we can come up with computationally cheap ways of getting confidence intervals, we should, by all means, be open to other techniques, move away from the Church of Bayes. And so we saw the beta Bernoulli bandit model, linear bandit models, neural networks instead of and other feature-based methods instead of using Gaussian processes, mainly because there's a sort of duality between features and kernels. So if you have kernels, there's techniques that allow you to map back to features. If you're in features, there's ways to map into kernels as well, of constructing positive definite kernels. And sometimes it all kind of depends on how much data you have and how big the parameter space is. If you have lots of data, you shouldn't be using kernel methods unless you have some really powerful techniques. And I think, are you going to talk about that today?
No, I talked about this week already.
Oh, okay. So you saw his lecture. I wasn't here. But he's already, so Mark's been doing some good work on that. But in general, if you're in the primal, if you're in the feature-based world, it's a lot easier to handle lots of data. You don't have to maintain a non-parametric sort of estimate of a covariance. On the other hand, if you have many parameters and very few data, and you know a lot about the smoothness of the function and so on, then you're much better off staying in the non-parametric world and using something like Gaussian processes. All right, so it very much depends on what prior knowledge you have in your hands and what constraints you have in the computation as to what models you use. But to me, it's clear, one thing is clear, that picking the right model is as important as picking the right acquisition function. So we tend to spend a lot of time talking about utilities and not enough time, I think, speaking about different models in Bayesian optimization. And as I mentioned yesterday, that was sort of my message for this class. Acquisition functions are, however, important nonetheless. And there's been a lot of very nice recent work. In general, what we're working on is maximum expected utility. So going back to for Neumann and Morgenstern, actually other people worked on this even before, but they formalized it nicely. Essentially what we're doing is we're trying to maximize the utility of some actions, X parameters, decisions, experiments. We're trying to pick the experiments that will retrieve some data, and when we're using a model with parameters W. And the Bayesian setting, the sort of Bayesian formulation of this, where W is considered a random variable from a posterior, that's sort of due to Savage, who I think was the first one to formalize this well. The book of Lindley on Bayesian statistics, it's a very short introductory book to Bayesian statistics, has a very nice account of this. So basically you need to marginalize over your parameters, over future observations, and your goal is to pick the best design or the best action. And so the only thing now in the setup to do is to design a good utility. And there's many utilities you could come up with for different problems. If your problem changes, if your problem is not one of optimization but learning a function, you could use, for example, this entropy utility, just explore the space. That's what's often done in active learning. And then yesterday we saw a bunch of other ways of, say, variance reductions in the Gaussian case, entropy reduction, and there was a paper that was mentioned about using mutual information and so on for active learning, and really there's a lot of things out there, but the main thing is they're all choices of utility. in reinforcement learning, where y, you could think of y as a vector that has many components into the future, you could get discounted rewards. So you can think of y as rewards, and you're obtaining discounted rewards. And you can think of you think an expectation over a trajectory. And what you're trying to choose there, your action is, say, the parameters of some policy. Often there, these y's might not be available. So they might just be available, say, after t steps, where t is really far in the future. So in reinforcement learning, so here in the myopic setting, we're dealing with these problems where you pick a set of parameters and you go and test them and you get an answer. Or you pick a set of parameters, you drill a hole, and you get your answers to whether there was oil or not there. But quite often in reinforcement learning setups, we have this issue that we're doing things, and we do things and do things and do things, and there's never a reward. And then, boom, we get there to see the reward. Okay, so like when you're playing chess and so on. In those settings, it's very hard to come up with utilities. And there's a whole field of people who work on things called intrinsic rewards that try to invent possible reward functions that will force you to explore the space. Or, as some even do talk about, how to be creative. Think of Minecraft. Think of what is the reward function for Minecraft. That sort of kind of gives you an idea of how coming up with reward functions is completely non-trivial. So we've seen a bunch of these type of utilities already. We saw in heuristics to deal with the fact that we can't compute these utilities fully. Okay, so this is getting, I wish I could move. It's not central, what's there. Anyway, these are the usual things. PI, EI, UCB. There's also, we saw Thompson sampling. We saw a few examples of Thompson sampling for GPs, for beta Bernoulli bandits, linear models. There the mechanism is you try to find the location of the optimum. So it's exact, and it will be more obvious in something that Phil is probably going to talk about. Entropy search, or Matt's also talking about it today. But you're sort of thinking about the utility of the function, trying to learn about the function. What you care about is learning about the location of the optimum. And so you would have to use a different, you have a different probability, is the probability of where you believe the optimum is. And then you try to minimize the entropy of that. Thompson sampling sort of tries to do that. It tries to also sample from where the location of the optimum might be. And the way we saw we do that is we draw a function from the GP, and then we find a maximum. That turns out to be easier said than done. You can do this if you have a GP over a space where you can only query at a finite set of points. Then doing that is trivial. I think Matt was one of the first to do that. Another thing that you might talk about, are you?
Yeah, I'm gonna.
Okay. So there's also, okay, I'm going to skip this then. There's also very cool sort of randomized algorithms for approximating this. And then Matt and everyone will also talk about entropy search, which aims at doing this. One important thing is that a lot of these techniques, when you compare them, like in a plot here that was actually generated by Matt, is you often find that a lot of these methods perform about the same. And as you change the applications, some perform better than others. For many applications, it's not going to matter which one you use. And for some applications, it's going to be critical which one you use. So it's good to know about them, but also don't feel that there's many other things that could make your Bayesian optimization not work. And there are setups where you can't use, for example, EI, where you have to go and use entropy search. So there's a few papers by Kevin Swirsky where he makes that case. There's also, there are also problems for which you know something more about the problem. So you might know the location, the height of the maximum. If you know that, you should do PI, using as the target the height of the maximum. That works extremely well and will do better than most other techniques. So there's some exceptions, but and you should know about these utilities, but don't get stuck only on that. There's a whole other range of problems in Bayesian optimization that are sort of very, very critical. And that's what I plan to cover today. So this is mostly work, and not so much even by me, but by people in this community that I would like to review for you guys. Since it's a summer school and so on, I thought I would give you a quick whirlwind tour of some of the problems that people work on. One of the first ones is hyperparameters. So we're using a GP with Bayesian optimization to tune the parameters of, say, a neural network. This GP itself has parameters, has, say, length scales if you're using matern kernel or something. If you pick those the wrong way, it doesn't work. So if you misspecify them in particular ways, you might have a kernel that will make it, and I'll show you an example of this, that might make you get stuck and never actually find a good optimum of the solution. And so we always, if you look at most papers, theory and experiments, they sort of assume that you know the hyperparameters of the kernel. And that can be dangerous. And so thinking about how to choose these hyperparameters actually turns out to be very tricky. And I think to a great extent, still an open problem. There's a theorem, and I'm going to distill from all this ink what matters. In this theorem, using EI, Z1 showed that if the hyperparameters, length scales, are between bounds, and if the bounds satisfy these Lorentz expressions that ensure that your deviation from the optimum vanishes, then you can get convergence. I think this with another result for the deterministic case, I think are the only two results that sort of show this, this vanishing regret when you don't know the hyperparameters. But to get that, both works have to assume these type of bounds. So you have to know something about the space. You have to know something about the smoothness of your kernel. By choosing the length scale, so if you make the length scale smaller, you sort of get more wiggly GPs, larger you get smoother GPs. And so if your function that you're trying to optimize, the real function is sort of very wiggly, and you're trying to use a GP that's too smooth, you're never going to hit on those peaks nicely. You can transform that theorem into an algorithm. And the point that I'm going to try to make here is not so much to say that that algorithm is a great algorithm, but rather to make the point that every method out there for tuning hyperparameters can fail if it doesn't, in the case where it's assuming that the function that is trying to optimize is not generated by a GP, is not, say, the mean of a particular GP. So whether you use maximum likelihood or whether you put a prior on those hyperparameters and are Bayesian and do slice sampling, if you model your GP is misspecified to the function, so even in this very simple 1D case where I have a fat sort of bump on the left and a thin bump on the right, if I run what I think is probably the best tool out there, Spearmint for Bayesian optimization, as iterations go by, here 6 iterations, what Spearmint does is we'll try to pick samples over there, and it's only because it doesn't have the right length scale to hit this optimal. So in this case, there's sort of 2 types of length scale. If you use the wrong one, you'll never have the optimum. So we do need some sort of adaptive scheme over those length scales that is smart. If you use bounds, and if you use some sort of, if you maintain track of what the posterior variance is, and you know something about the variance of the noise, you can sort of control those bounds over your parameters, and it is possible to get convergence. So it is so the point here is that it is possible to design algorithms that are robust with respect to this type of specification. But this, I think, is by and large an open arena. The issue of optimizing acquisition functions is also interesting. Quite often it's just mentioned as a little remark, oh, we used CMAES or direct, or we use Latin hypercubes and then we follow the gradient for a few steps. So there's many sort of heuristics. And as I mentioned yesterday, even if the heuristic fails at one iteration, if you're doing multiple iterations, you somewhat recover from, you may recover from this. Most of the theoretical papers also, they give you a vanishing regret, assuming that you're able to find the optimum of the acquisition function, which is in itself an NP-hard problem. So the type of theory that we have is regret vanishes provided you can solve an NP-hard problem. It's somewhat not satisfactory. And often something about a theory that it's going to be useful to understand how these methods work is if we look at the deterministic case, this is the case where the function, you measure the function and you don't get noise in the measurement of the function. So in other words, where you make an observation, the upper confidence bound here in black and the lower confidence interval, the difference goes to 0 because you have a deterministic observation. Now here I have a cost function, which is this thing in blue, and the red dotted dash line is the GP mean. What I'm showing here, that point is we've observed the function at 5 points in the boundary in these 3 points. And that green line is the height of the most successful point, or the highest point at which you will find this magenta lower bound. If you believe in your prior, so this is a probabilistic Lipschitz at work. If you believe that the function is caught in these intervals, in these confidence intervals, then it must be that if you lower bound, you can achieve at least that lower bound, that anything where the upper bound is lower than that highest lower bound should be discarded, because the function will be trapped here regardless. So we might as well just prune this whole part of the space. And that's in a sense why global optimization works, why these confidence bounds work, because as you're sampling, you're actually really discarding huge parts of the space. Now, one can use that intuition also to design algorithms that sort of move away from you having to maximize some acquisition function, having to solve some NP-hard problem. And what sort of makes us believe that this is possible is work in the pandas literature, especially by Remy Munoz, where, and also sort of in the games, sort of game tree literature, where people have shown that with very weak assumptions about smoothness of functions, non-global, so without the lack of global assumptions and so on, it is possible to optimize a lot of these functions. It's possible in the sense that it's possible to get the same type of regret functions. People use tree-type methods. This is called optimistic optimization, because you sort of, if you're doing well in one branch, you keep sort of expanding that branch. It's sort of, imagine this as trying to go for the frontier of where you're doing well all the time. And then it's only when you get stuck, you sort of backtrack and you push another frontier. The problem with these methods, though, is that as you expand, and essentially what we're doing here is I have this 1D function, and every time I expand, I evaluate the function at this point. So at this blue point, I would evaluate. So we're sort of partitioning the space with it, and then evaluating the function at the center of that partition. If you have a prior, now imagine you have a prior over the structure. As we branch out, following the same type of algorithm, then it's possible to, in regions where that's sort of at least in the deterministic case, where the lower bound is higher than the upper bound, there's no need to evaluate the function there because you know that you're not gonna get useful information, but you still need to expand it because it might be that in the subspaces, if there's non-stationarities, an optimum may be found. So the advantage of this, and here it becomes very clear what the advantage of bringing a prior is. A prior basically gives you this extra knowledge that there are parts of the space that you don't even need to explore. So your prior knowledge is telling you this. So it gives you room to build much bigger trees for the same computation. So in fact, I think these two trees, this one and this one, were built with the same amount of computation. And in doing this sort of expansion, you can get bounds and so on, but you're not relying on having to solve an NP-hard problem. And I think more of these type of optimistic methods, again, would be something that would be nice to explore. They're very successful in games and so on. So, conditional parameters. I'm going to come back to this, but when I talk about random forests. But one of the big problems in tuning hyperparameters and saying packages like Torch that use these neural networks and so on is that until you instantiate a layer, a particular module, you don't know what parameters it should have. So which parameters use as sort of condition on what it is. Also, for example, if you're making categorical choices as to, for example, what kind of basis function you should you use a ReLU or should you use a sigmoid? That depends on how many neurons you have. If you have only, say, for MNIST 10 neurons, you should use sigmoid. If you have 100, you should use ReLU. So some choices depend on other choices. Very little is done in this area. There's been a couple of papers, but this is an extremely hard problem, and it's an important problem. Like, this is the one we want, I think companies would like to see solved, because almost every software that has many components, there will be a mix of continuous and categorical, and they're all conditional. Sorry. Another thing that really matters a lot is non-stationarity. And so you might have a function that's like this. That's we already saw with the bumps. Like if you have thin bumps and thick bumps, you can get yourself trapped in the thick lower bumps. But if you have non-stationarity and you assume that you're going to use a Gaussian process with a stationary kernel, then obviously it's not going to work well. And it turns out that in practice, at least I think this has been experience of Ryan Adams and all his team, and certainly it's been also my own experience, that a lot of the problems that we try actually do have some element of non-stationarity. So it's good to already, as you attack these problems, to be prepared to have in your bag, in your toolbox, ways of handling non-stationarity. Spearmint has a very nice way of doing this, which is warping. There's many ways of doing warping, but one way to do it is, if the function is non-stationary, if this is the original function, let's call it x, the inputs are x, what we do is we put the inputs x through some sort of transformation, like some sort of CDF, for example. And in the transform space, it will be one of these curves. In the transform space, we get a stationary function. And so then the question is, what shape should we give this function to be able to do this? And the way Kevin and his colleagues are doing it is they introduce these parameters alpha and beta, and then they optimize and they estimate these parameters as well. So as to basically estimate the right type of non-stationarity. And this always and invariably gives him better results. And I found that this also for us, for a lot of problems, always improves things. So non-stationarity is definitely important. That's one way of handling it. Another way of handling it that is sort of especially important when you're doing gas exploration and so on, because there's like faults on the Earth, as is shown in that mining 3D volume. And if you have faults, you really have discontinuities. So you have things like you might have like in this case, where you might have a GP that so here the actual function is in blue, and so here is fairly, and to the left here is very smooth, and then it becomes very wiggly over here. Now, if you just do Bayesian optimization, which is the top row here, as you're going, because even if you're learning the hyperparameters, you might just be learning about the smoothness of you've taken most of the points, and so you end up not doing well here. Whereas if you introduce a tree method, kind of like the ideas that we saw yesterday when we were talking about random forest, you can start splitting the space, and then in each part of the space you fit a GP. And then because you're fitting different GPs with different hyperparameters, you're able to fit a GP with smooth parameters there, and then you're able to fit a GP there that has higher variability. I went very quickly over this random forest thing yesterday, and I think there were a few blank pages, and a few people asked me a few questions. So random forests have a very nice property, or trees. Actually, a random forest is just an average of trees. That's all it is. So you compute all the GPs, and then you would average the decisions, the predictions of the GPs, and that's basically what a forest is. It's just a bagged estimate. But when you construct a tree, let's think about just constructing a single tree. And just to illustrate this, because this actually turns out to be very important for conditional spaces, I'm going to construct a tree. Here I'm showing 4 steps of doing it. And I couldn't find a nice picture for regression, so this is for classification. But for regression, it will be the same. It's the same thing, except that instead of fitting a classifier, you're fitting a function to it. But let's suppose we wanted to do this problem of classification, where we have 3 classes, red, green, and blue. And we also have 3 features, x1, x2, and x3. So our features, x1, x2, and x3. So you should think of, suppose you were using Bayesian optimization to tune an algorithm. So think of x1, x2, and x3 as the parameters of the algorithm that you're tuning. Okay? So you have 3 parameters to tune. The way you construct the tree is as follows. At each node, we start at the root there, and the root is in yellow. The current point that we're going to be working on is going to be in yellow. And then the point that we're done working on will be in dark gray. And then the point that we will proceed to work on next will be in light gray. So let's suppose we're at the root. What we can do is we can sample. So this is a particular variant of random forest due to Bryman. And let's see, which version is this? This is CART. What you do is you sample a subset of the parameters. And so what I'm doing here is at each iteration, I'm subsampling 2. At the top, I'm going to sample x1 and x3 at random, so uniformly at random. So I drop x2. And I'm going to do this with replacement. So at the next iteration, I could sample the same guys again. And then I sample each of them, and then I do a projection into those dimensions if I'm doing classification. And then what I'm going to do next is I'm also going to sample, I can also sample some points at which I'm going to split the data. So that can be, I can either sample that or I can estimate it. If I were to sample, we would get like what people call extremely random forests. If I was optimizing it, I could use something like entropy. And actually, I've got a slide next where I'll show you where you could use, you have some cost function and you're trying to minimize, you're trying to achieve some reduction in entropy or to separate the classes. So in the first iteration, I look at x1, I look at x3, and I use one of these tests that are routinely used for constructing trees, and I pick the yellow arrow as the good split point. So in other words, to expand a node, I need to do 2 things. I need to select a subset of features, and then I need to use a split point. And the split point is what I partition. So these are the split points for a GP. And then for a GP, instead of trying to fit a classifier, what I try to do is fit a function there. And so on, I proceed to do this. I might decide not to split the point 2. So I have that choice when you're constructing the tree. And I can sort of proceed to do that. And at the end, I will have a nice split of the space. Now, the important thing about this is that as I'm sampling parameters, I'm only looking at the subsets of dimensions at a time. And in fact, if I start now constructing sampling mechanisms that are not uniform, but where I actually do maybe pick a subset of 10 out of 1,000 features, and I optimize over those 10 to see which is the one that will give me the best separation, then I'm effectively picking which is the parameter that's most important, and how should I tune my random forest to deal with that parameter. So if there are dimensions that are irrelevant, if there are parameters that are irrelevant to the optimization process, I'm going to be dropping them. Moreover, this also somewhat handles conditional parameters, because I can pick some parameters and in a way that I will only pick them if I've already selected some other feature. So if I've got a layer, then I will worry about choosing the number of neurons. Otherwise, I won't. So trees have those advantages. And SMAC, the method of Frank Hatter and his colleagues, it takes full advantage of this. And because of that, they're able to handle spaces that have like 200 parameters quite easily. And they're also able to do this in conditional spaces. So there's a lot of promise there. However, there's also problems there, because they have to use frequentist estimates, and quite often in the naive optimization problems, the GPs, I believe, tend to outperform the random forests. In fact, the original work I did with Eric was also all on random forests, and we abandoned random forests because of that, because of not being able to get good confidence estimates. However, that doesn't mean that that's the wrong route to go. I think it's just there is need to get good confidence estimates for these three methods. So if you have ideas and you can improve on this, then you should by all means do it. For regression, here is a particular way in which you do a split. So you have a feature vector x, and if it's above this value, you send it to the left, otherwise you send it to the right. And often the way we split these trees is we have some criterion, like the reduction of RMS as you're fitting the GPs. So you try to get a good fit over the entire space. And you might be fully Bayesian on each leaf of the tree. You can use different types of GPs with different hyperparameters and so on, different types of functions. Or you can use just like what was most popular, which is just to use a DC level, so sort of a particular height. There's reasons why one would want to do this, because if you're in very, very high dimensions and you have very few data, you might not want to try to estimate very fancy functions, because you don't have the data to support that, unless you have very good priors, or unless you have a way of aggregating information from other regions of the space. As you're constructing trees, when you start doing Bayesian optimization, there'll be things you have to do that are different than when you construct trees to do classification as well. Like a very simple thing is, like, for example, is the CART criterion, which is very popular in classification, which works really well, basically tells you pick the split point between the 2 points. But if you do that, what you get is you get this sort of variance increasing. And in fact, there is, Bobak made that mistake recently. And I can show you how bad it gets. Yeah, here. See, at the boundary where it splits to another GP, there is this blue spike. That's a spike in variance. So whenever you have these boundaries, you'll get your variance exploding. And so if you're doing expected improvement or UCB or whatever you use, you'll be always picking points at those boundaries. So this kind of thing is very dangerous. These are things that are very simple in retrospect and that look obvious. But when you're running the code, unless you're being very thoughtful about what you're doing, you could very easily make these very simple methodological mistakes and your code will not do something reasonable or will be suboptimal. One very simple fix for this that John Assel came up with was to, instead of splitting in between, like what people do for classification, is just always split at a point and make sure that that point gets added to both leaves. Very simple idea, but for us it meant a huge change in performance. So sometimes it's in the little details where it's the little details that matter. Another thing that John tries to do with his trees is that because you're building at the leaves, you're fitting GPs at the leaves, the problem of splitting, breaking the space, and then trying to fit the GP by estimating its hyperparameters is that in each partition you'll have less data. So if you're in a setup where you have very few data points, that's not very sound. And so you somehow need to aggregate information from the other leaves. And he tries to come up with schemes to aggregate information over the tree. This is very similar to what Bayesian statisticians do in a hierarchical Bayes. Like if you're trying to make a decision to operate a patient and at a particular hospital, that also depends on the decisions that other hospitals made. So you look at these aggregate statistics to allow you to make local decisions. And when you do this, when you use the sort of tree methods, that sort of is just Bayesian optimization, but now where you add a tree to deal with non-stationarity. On many applications, we tend to observe an improvement in performance. So here the treat methods are the red and green. And yeah, John threw this at a bunch of things, and you do get a significant improvement in performance. And the same thing you get to observe if you do like warping and so on. So non-stationarity does seem to be especially an issue in a lot of these hyperparameter optimization problems. Another thing that's sort of very important, and this just going to go very quickly over it because David's here. David was here. Oh, so he is the one that really does this work, so you should talk to him. But the idea is if you're doing say a hyperparameter optimization in the Borg or some big cluster, you're running a lot of these jobs. Some will have finished, some jobs won't have finished, but because of correlations and so on, you can already predict how you believe the other jobs will do. And so you can already use those predictions to augment your data set to make decisions. And I think that's the gist, more or less, of what David does. And of course, the devil's in the details, and you should look into that. But it's very interesting stuff. It's very important, too. This idea of like very quickly forecast whether something is promising or not and decide to switch is very key, because you could spend a lot of computation rolling that process to the end. And that's actually one of the main impediments toward companies adopting Bayesian optimization. It's because computation actually does cost a lot of money. Amazon measures things in watts, algorithms and so on. Another important area, and here Bobby Gramercy at NIPS actually gave a very nice talk on this. I'm not going to make it any justice here, but quite often you also do Bayesian optimization with constraints. You might want to optimize, some fluids in some ODE type model, but you're subject to some constraints as to where the fluid's allowed to go through and so on. And usually people handle this by introducing extra functions like this H. So they modify, say, for example, in this case, the expected improvement by adding these functions that could be, say, binary. 1 when you're okay, and becomes 0 when the constraint is not being satisfied. And then you sort of try to sort of estimate a latent GP that will have these binary observations. Other things that folks do is, for example, scale expected improvement by some computational cost, say time. Again, there's quite a wide literature in this. And I don't think there's, in general, still a clean way to do this. So another nice research area. High dimensions, yes. Random forest, one way to attack 200 dimensions and so on. Another way to attack it is, sometimes, not always, but sometimes, is to exploit randomness. In fact, the most popular Bayesian optimization technique right now is use a random grid for your in terms of hyperparameter optimization. Random grids turn out to be actually quite effective. They're definitely, whenever you try a technique, make sure that you have that baseline, random search. You have to do better than that. And I mean it. Quite often we've tried things that and then you try random search and you go, dull. Because, yeah, it's... So something that provides a bit of intuition is, think about this function here. So one of my students, CEO, tried to exploit this idea of the effectiveness of randomness in optimization and tried to combine it with some tools for optimization. So there are some functions like this where one of the parameters does not really change performance much. So if you move along x2, the value of the function, if you're at a particular value, will not change dramatically. But if you move along x1, the value of the function changes dramatically. This is like when you have two knobs, one knob matters, one knob doesn't matter as much. If that's the case, in a sense, the problem shouldn't be two-dimensional, it should be one-dimensional for the optimizer. So Zio's idea is then, let's just search along one of these random diagonal directions, and let's search in this 1D space. So instead of searching in this 2D space over x1 and x2, we're just going to search over here. And then if you follow the blue line, you will intersect with the dashed green line and find the optimum. So that's the idea of embeddings. And you can do this. Random is just very easy. You can try to learn the embeddings, and Andreas Krauss tried to do that, but that actually turns out to be expensive. We still don't have practical ways of doing it, really. And the idea of, so that's basically Bayesian optimization. We maximize the utility, we get more data, refit the GP. Random embeddings is exactly the same thing, except what we do is we optimize in low dimensions, and only when we need to evaluate the function, we project with a random matrix to high dimensions. So you do your optimization in low dimensions. When you need the evaluation in high dimensions, you multiply by A. A is sort of like tall and skinny, so it will make this a big vector X. And then you evaluate f of the big vector X. So you're trying to optimization along a manifold. Sometimes this works, sometimes it doesn't. It depends on the type of function that you have. When it does work, it's pretty sweet. So Zio's tried this in some optimizers, like for combinatorial optimization, and there it outperforms state of the art, SMAC techniques and so on. It's a very simple trick. It's worth. The beauty of it too is that because you're only optimizing low dimensions, you can always do that optimization with Gaussian processes, and then the evaluation is in high dimensions. So you can go easily to 1 billion dimensions. In fact, you can go to 1 trillion or 1 quadrillion dimensions. There's no limit in the dimensions because the intrinsic dimensionality is small. Another problem that sort of, we already saw this yesterday, the issue of multitask or multiple outputs. And for example, you might have a problem where it's cheap to evaluate a function. There's some cheap way of evaluating your designs, but it's sort of very high variance. So you don't know that it's a reliable design. So something tells you, I believe that what you're doing is good, but there's high variance. So you can ask, for example, one of your friends in school, am I doing the right thing? And your friend, so that's low cost. And your friend gives you an estimate, but of course that's not as good as the estimate of, I guess, the professor or the TA marking your exam. That will be a more expensive test. Thanks. So the idea of multitask is to try to take advantage of this, that you could have different outputs with different reliability providing with feedback. Kevin Swirsky already has done some work on this with kernels, and just to illustrate, this is one of his pictures, where you have 3 functions, and then for the blue function, we're looking at 2 fits. This is one fit where we model the correlation between the tasks. So we've only observed these points. Here we don't model the correlation between the tasks, and we try to fit the blue function, so you'll get this fit. But if you do model the correlation in this area between these points, where your observations are, you do get a fit that is more like the original function. So, you exploit the fact that commonality between these different tasks to do well. The way he does this with GPs is by introducing these product kernels, where you have a kernel over the X space, but you also have one between the tasks. So similar tasks. So in a sense, it's kind of like augmenting the kernel to also look at similarity over tasks. Of course, we all know that you can also do Bayesian optimization in the primary with features, and the literature on multitask is vast. So there's lots of stuff you could go and do in order to deal with context and different tasks and so on. Another idea that's very important, it sort of already came up when I was discussing parallelization, is the fact that the way people tend to tune, this is especially relevant in hyperparameter optimization, where you see there's a lot at companies where people are running optimizers to tune a model and trying different variations, especially nowadays with the software is very modular. If you want to construct a deep net, you have a bunch of modules with a bunch of settings, and it's just a question of putting them together. It's like Lego, really. And so you just want that Bayesian optimization to come and sort out the Lego for you. But each of these runs, you throw in, 1,000 GPUs at this, and that takes like sometimes a week or 2 weeks. So even with all the large-scale resources, people are really hitting problems of consumption of energy and so on. So what we see humans doing all the time is sort of cutting if a run is not being successful, they cut it earlier and so on. And there's been a few works. David's done some work on this. He's here, you can talk to him. Kevin Swirsky has also worked on this with colleagues. Frank Carter had a nice paper this year at ICHCAI, where they all try to, either via modeling a kernel over these curves, as in the case of Kevin Swirsky and colleagues, or through use some sort of more parametrics primal way with random forest, they're trying to solve this problem. This one is extremely important. They have partial solutions to this problem. But doing this well is, I think, one of the biggest challenges. Because this idea that you're going to try all the experiments and then pick the best one, it's just not practical. We really have to be able to sort of do these forecasts and stop early and so on. Another thing that's sort of critical is when we do Bayesian optimization. It was upstairs yesterday. You always choose the bound over where you're optimizing. Typically, you do it over a compact set. This happens used to happen in my lab almost every year. Every time there's a new student telling me that it doesn't work, quite often what you find is that they've chosen the box wrong. So the question of the size of the box is a non-trivial one. Because if you choose it too small, you might miss the good or juicy parts of the space. If you choose it too big, you're just going to be exploring. So Bob Shahriari has been recently looking at ways of handling this, in particular, ways in which if you choose the box, how can that still allow you to grow over time so that you don't miss the optimum. So you start with a box inside, but you can sort of expand it. And Okay, we have. This is still very. It's like that. This is still very. It's a precarious area choosing these boxes. It's the current set of technologies sort of describe what just happened there. It's something that needs to be addressed. Another setup to finish, and I'll just say it in words. And this is something that the people that work on SAT and combinatorial optimization always do, where you sort of think bigger. You think what you have is a bunch of problems. And these problems have features. And you have solutions, or algorithms in this case. And those solutions have features. And those solutions might also have hyperparameters that you need to tune. You need to sort of tune the solution to a particular problem. And so one of the ways to do this is to try to think of, and this is sort of somewhat like the contextual, but instead of trying to do everything online, you can sort of pre-compute some stuff. You can, for example, try to estimate features of the problem, and based on the features of the problem and the optimizer that you use, try to forecast how long it takes. So this is what they do in SAT. So for different SAT instances, they try to understand features of SAT problems. And it's sort of relevant because you can reduce SAT to Boltzmann machines, which can then be reduced to autoencoders. So you can very quickly get the transition to what people do in machine learning via SAT. And so you can sort of try to pre-learn things about the problem. You know, you can try to be a bit more human, I guess, human-like, where we sort of, for particular problems, we use some solutions. For other problems, we will go and use some solutions. And if you learn to sort of predict how well your methods are going to do, then the part of Bayesian optimization is only once you pick a technique, a solution for a method, then you fine-tune it with Bayesian optimization. So you do sort of a mix of identifying solutions through features, through representations, and then you do some other step, which is the fine-tuning. I think that approach has been extremely successful in SAT. So successful that they had to stop going to the competition because they were just winning it all the time. We might see a lot more. I would love to see more of this on Bayesian optimization. That's pretty much it. Thank you. And if you're finishing your PhD, they paid for the trip.
I would have a question about the tree-based methods you mentioned. Maybe I didn't understand this correctly, but actually two questions. So one thing was, I think I understood correctly that your splitting criteria is kind of based on actually evaluating a Gaussian processes model at the potential nodes. Is that true?
Yeah, at the nodes that you.
Then imply that you have to do this much more often, so that you get a trade-off between your, not using that approach and getting worse results, and using this approach and maybe getting better results, but with a lot of additional computational effort.
Yeah, the computational effort of fitting a random forest is dealing with fitting a tree is not significant. Especially with the particular criterions that were being used, just RMS, with a few points, it's that fast. That's not an issue. I don't think the computational cost here is significant.
But you get more, you have a model at each leaf, right?
You do more computation, but I would argue that you do more computation, but again, I would argue that in the kind of setup, this would be like if you're fitting GPs, this would be relevant if you're in a setup where you have thousands of millions of points, in which case I wouldn't be fitting GPs, I would be fitting some sort of parametric model. And that would be quite efficient. If I was doing GPs with that many points, it would be problematic. Yes, even though, again, as I said, I wouldn't do it that way. And even what tends to happen in practice is in these type of optimization problems, I mean, is that we're not dealing with a case where we have, very rarely are we dealing with this like 1,000 evaluation points. And if we were doing that, I wouldn't use a GP, I would use something else. But usually you do, 1,000 will still be fine. But if you're dealing with, a few hundreds of points, as we often do, I think we're kind of fine. The computation is, again, not a bottleneck. Building a tree, fitting a tree to data is really efficient. It's not.
No, usually it is, but my understanding is that you have to run an optimization step for that. But maybe that's a misunderstanding. So how do you find the splitting point?
The splitting point?
Yeah.
Oh, these splitting points are very easy because you just go over the data points.
So you use just a
Yeah.
tree splitting criteria.
Yeah, you could go over the data points. That's enough. In fact, some people just go random.
Right. Okay.
Whichever you go, building random forests is efficient. And I'll tell you a secret. Most startups, most of these things that recommend you friends and so on, they're either using boosting or random forests. Because they are that efficient. They are that efficient.
Normally, your data points are not the things where you have to evaluate across the function, right? I mean, that's the difference here. Okay.
Maybe we can take this offline.
You were mentioning warping of the input space. So in general case, you will have non-Gaussian likelihood. So that
Yeah.
basically introduces a need for an approximation, right? So is it that it's better to deal with having to do an approximation rather than non-stationary kernel?
It's certainly what folks have found. I mean, it's certainly it's certainly what we have found every time we run Spearmint. And that's not the only approach. There's a whole family of techniques for dealing with non-stationarity. So like Salmon, Goodthorpe, and so on. In general, I would say yes, you do need to attempt to model non-stationarity. It's certainly what we've been learning in practice is it's very hard to talk about these methods in a way because they all depend on the function that you're optimizing, and you don't know the function that you're optimizing. So this is all almost like faith-based choice, choosing what to do. But certainly for the functions that we've tried, that sort of appear in our papers and so on, it is quite often the case that they are non-stationary. And so doing the step of actually modeling non-stationarity pays off.
And do you have some preference in terms of the approximation method that you think works much better than the others, or it's not such a big deal to choose the method?
I haven't done an extensive comparison of these different type of warping methods. I think Kevin Swirsky might have. His thesis is...
about the approximation to Gaussian likelihood?
You'd have to ask Kevin Swirsky what all his approximations are and how they work.
But if you do input
but
warping, the likelihood is going to change.
Yeah. So in input warping, you're just doing optimization of these parameters. So you still use a Gaussian likelihood, and then what you do is you optimize. You treat these as hyperparameters, and then you do maximize this Gaussian likelihood, or do slice sampling. I think is what they do.
Input warping just makes the kernel non-stationary, but you could use a Gaussian likelihood with that, or you could use a non-Gaussian likelihood with that. These are just sort of parallel. These questions.
Yeah.
You could use one thing to model the non-Gaussianness of the observation model, and you can use this to model the non-stationarity of the kernel.
Okay, I think my point was more like if at the beginning you assume that Gaussian likelihood describes your input well, then when you add another function and you change that, then basically you start to functions that you will generally have non-Gaussianity. But what you're saying is that you totally forget about what your inputs were at the beginning, And you're saying, well, I can still use Vision library.
Yes, I think so. This might it might require taking this a bit offline.
Yeah, but there's many ways of doing this. Luke Bourne's PhD thesis is actually on this, on heteroscedastic and non-stationary GPs. It's a good resource. It's certainly a good resource for references, and of course Kevin Swarsky's paper, where we can maybe continue. I'm going to pick.
Yeah, I can read maybe one more. I have two questions. First, get up. So, could you give an example where the intrinsic dimensionality of this hyperparameter space is fairly small, so we can use this lower dimensional embedded?
Again, we're back to religion. You have to have a leap of faith. And so what you do is you try, and if it works, it works, and if it doesn't, it doesn't. One example was one that I had yesterday, which was the LP solve. A few people have tried other things. Andreas Krauss has some examples and so on. One that I was pretty happy with to do this mixed integer programming. So there we got better performance. And because this package is used a lot, we were very happy that we could improve it.
Okay, and a second question, very quickly, maybe a bit silly. Would there be any benefit in trying to replace, for instance, stochastic gradient descent with Bayesian optimization for training V parameters of a neural net?
No. Definitely no.
This is wonderful. I think I can take away from there. I'll talk about this in my talk. So because the
Oh,
talks
that'd
are
be
quite long and the breaks are quite short, I think we should stop on time. We have a 15-minute coffee break I just saw in the program that was handed to me an hour ago. So we'll start again in 15 minutes, 10:30.